Okay, so in this video, we will discuss the issue of training set size. Apologies, there's a little bit of an echo. I hope my voice is still clear. I should say that this issue is a little bit complicated, and there's more than one perspective. However, I should make one thing clear. The question is never, am I using too much data to train? The question should always be, am I using enough data to train? You can never use too much data as long as your data is good quality. If your data is poor quality, you may degrade your training. But as long as the data is good quality, unbiased, representative, and so on, more data is always better. So the question again is, do I have enough training data to ensure my model is good? So as I indicated, there's more than one way to go about this. But the basic idea is you will vary your training set size and see what happens to your model. So you may take a range of training set sizes and train for several values of training set size within this range. And you'll record your cost function and your cross-validation cost function, and you'll use that information to determine whether your data is enough. And you can do that graphically. The basic concept here is convergence. If your cost function and cross-validation cost functions are converging, then you know that you've reached a suitable amount of data, and more data is not going to change your model very much. So as I mentioned, you take a range of training set sizes, and you're going to plot the cost function and the cross-validation cost function as a function of this. So how do you diagnose the result when you graph? Well, in this case, your error is actually increasing. And the reason it's increasing is if you have more data points, it's more difficult to fit them. Right? So if you have just one data point, it's easy to fit that. 2 data points also very easy to fit, and so on. So in this case, your cost function is increasing. But it's going to stabilize. Eventually it stabilizes. Now when you do cross-validation, that's a different story. Because this model that you fit with one point fits very well for that one point, but then when you do cross-validation, it's going to perform terribly. So your cross-validation is going to come down. So eventually, both your training and your cross-validation cost functions should stabilize. Now, once they've stabilized or converged, that's an indication that more data is not going to help you anymore. So that's really what you look for. You look for stabilization or convergence. Another thing you can look at is when you do cross-validation, for the different folds, you're going to get different models. If those different models all agree, then you have a pretty good idea that you have enough data, that you're getting the same result, even when you take part of the data, and you're getting consistent models. So that's another thing you can look at. And I point out the added complication that you're doing this with a particular model, and there's still a question whether this model is overfitting or underfitting. But we can deal with that question also looking at these same curves. Right, so this kind of plot is called the learning curve. And in general, this is what learning curves may look like. You may get cases where the training fit doesn't increase steadily like this, but sort of bounces around. But you are looking for this feature of stabilization. Eventually, they should stabilize. If it's not stabilizing, you probably don't have enough data. Now, we can also use these curves to diagnose overfitting and underfitting. Remember that the point here is that you want your cross-validation cost function to be small. that's really what you want. And if you do have bias or overfitting, it will show up on this curve, as we'll see in the next few slides. For instance, if the model does have high bias, what do you expect the learning curves to look like? Well, suppose you fit a straight line model. As you fit more and more points, the model will become basically worse and worse because you're asking it to fit points that are not on the trend. But it will eventually stabilize. And the cross-validation will also stabilize similarly. But both are very large. And they are agreeing well. Essentially, they're equally bad. So that's what you'd expect for underfitting. Now, if you have learning curves like this, more data is not going to help. Basically, you need to change your model if you want to get better performing model. So go back to the drawing board, add more features, or change your model in some way. Machine learning is an iterative process. So you can add new features, add higher order features, add combinations of features, or try a completely different approach. All right, now suppose we have overfitting instead. What do we expect to see? Well, if you have overfitting, and you're using that on little data, you expect the model to perform very, very well. You're going to have very, very low error. But eventually the error will increase as you get more data, and it will still stabilize. But then how about the cross-validation? You're going to see a gap here because the cross-validation is not going to fit as well as the training, because you're basically fitting too well on the training and you're picking up detail that's not really there. So eventually the cross-validation will stabilize, but you'll have a big gap. So it's the gap that shows you the overfitting. So we saw that before in our previous discussion of overfitting. Basically, cross-validation is a reality check. Is the performance I'm getting for the training set really representative of what I'll see on new data? Now, what do you do if you see a big gap? Well, if the cross-validation score is still decreasing, it's possible that you're not actually overfitting, but you just need more data to fit the parameters. Okay? So if you are continuing to have cross-validation decrease, then you should try to get more data until it stabilizes. And so as I said, the key here is stabilization. Once things stabilize, that tells you you've reached an appropriate amount of data. So ideally, you'll want to get enough data to have this stabilize. However, in practice, data is often very hard to come by. So what happens when you really can't get more data and you still have a big gap? Well, that means that your data is insufficient to train the complicated model that you're trying to put on it, and you should consider either regularizing or reducing the polynomial order and get a simpler model that's appropriate to the amount of data that you have. All right. And, but the best option is to try to collect more data and see if you can get a better fitting model. Okay, that's the end of this discussion. Thanks for watching.